just look at A. Do you think that's a strong acid or a weak acid? Or a strong or weak base?
Weak base.
It's a weak base. Why?
Because it doesn't have any hydroxide ions in there.
Really? These red and white things are actually hydroxide ions.
The size of the molecules are small. Is that anything to do with it?
So this might be hard for you to see, but this molecule has a blue, and then there are 3 whites. That one has 3 whites. That one has 3. That one has 4. So if it has, most of them have 3, and one has 4, what does that mean happen to the number of hydrogens in this one? If it's normally 3 and it has 4, did it gain or lose a hydrogen? It gained a hydrogen. And what gains hydrogens? Acids or bases? Bases gain hydrogen. So this is a base. And how can you tell whether it's strong or weak? Has to do with how many of them gained hydrogen. Only one of them did. Because there's 2 of these, I'm guessing one of these other ones has 4 also, but I can't find. Maybe, it looks like maybe that one. But only some of them have 4. That means it's a weak base. If it was a strong base, they all would. What about this one? Do you see one of these yellow ones that looks different than the rest?
No.
It may just be too far away.
Yeah, that one doesn't have.
These all have one white one. That one doesn't have a white one. What does that mean? It's a weak acid. That one lost a hydrogen, so it's an acid. And because only one of them lost it, it's a weak acid. You can also tell it's an acid because there's this right here. It's H3O+. What is H3O+? That was in the video.
Hydrogen carbon.
No, H3O+. Hydronium ion. So we said that it's very, very nice for us to think about hydrogen, H+ ions floating around in water, but they don't do that. As soon as they get released, they bind onto a water. You would take H2O and add H+, you get H3O+. So this is hydronium. So seeing that will tell you it's an acid. What about this one? What do you think that one is? First, is it an acid or a base? Do we have hydroxide ion or hydronium ion? These are H3O+, that's hydronium, so it's an acid. Is it strong or weak? It's strong. These were hydrochloric acids. There should be a hydrogen on each of them, but they all lost it. So this is a strong acid. The acids that we've talked about have been HF, HCl, HI, and then HBr, hydrobromic acid, that fits right in with them. But not all acids are what we call monoprotic acids. A monoprotic acid is an acid that only has one hydrogen that it can give away. Some of them have more than one, and we call them polyprotic acid. Poly meaning more, or more than one, multiple. These are some examples of polyprotic acids. What is the name of that? We learned this a long time ago.
Is it phosphoric?
Phosphoric. When you have a polyatomic ion, you don't put the hydro in front. So this is phosphoric acid. What about this one? What's this one called?
Carbonic acid?
Actually, that's very good. I was actually skipped that one because I didn't figure anyone would know that. What about the bottom one? The bottom one was on the list that you had to memorize. You have to memorize that. That one's sulfuric acid. So this one has 3 hydrogens, this one has 2, this one has 2. Those acids can give off as many hydrogens as they have. But they come off one at a time. It's not that this one just spits off 2. One will come off, one will react, and then the second one will react. So here is an acid-base reaction. And we need to figure out, just on the reactant side, which one is the acid and which one is the base using the Bronsted-Lowry definitions. What was the Bronsted-Lowry definitions? This was the one that had to deal with accepting and giving a hydrogen. Bases gain, yes. Bases accept a hydrogen. Acids give away a hydrogen. So you're going to have to look at these reactants, and then look at the products, figure out where did these come from, and then figure out, did that gain or lose a hydrogen? So if you find this over here, which one of these did that turn into?
First one.
The first one. You have the OCl, and you have OCl, right? Did that gain or lose a hydrogen when it went from here to here? It gained. So if it gained, is that an acid or is that a base? That's a base. And so, if that one is a base, by default, that one has to be an acid. These types of problems, you have 2 choices. You can either figure out, do I want to find the acid, or do I want to find the base? And if you can find one of them, the other one is process of elimination. To me, it's usually easier to find the base. Which one went up a hydrogen? But if we look at this, did this lose a hydrogen when it went from here to here? Yes. You take a hydrogen away from that, you have HO, but HO is the hydroxide ion, which we write OH. So this one is our acid. Which one here is our acid? Which one is our base?
The base is the F.
Right. The base is the F. Here we have F, here we have HF. So it went up in hydrogens, it's the base. By default, that's the acid. What's maybe the even easier way to do that one? Or to know the answer to that one? What's the name of that? We just did it. What's the name of that? Sulfuric acid. Sulfuric acid is not a base. Sulfuric acid is an acid. What about this one? Which one is the acid? Which one is the base?
Ammonium.
Or it's
Ammonium is the acid. Here we have NH4, here we have NH3. It went down a hydrogen. Did this gain a hydrogen?
Yes.
Yes.
So water can be an acid or a base?
Yes. In multiple ways, water is the weirdest molecule we'll ever deal with in this class. We're going to come back to that later on. That's the whole basis behind pH. So here we have a reaction. Here we have a reaction going just as it's written here. And as it's written, which one is the acid, which one is the base? The acid is the HF. We went down. This one is the base. We stuck a hydrogen on the front. So that one's the base. Now, imagine I took this reaction and I flipped it around so that these were our reactants and these were our products. Which of these would be the acid?
HCl is the acid.
HCO3 would be the acid. Because here we're going from this to that. It lost the hydrogen, so it is the acid. This gained the hydrogen, so it's the base. So we take our acids and our bases on the reactant side, and we can label on the product side what we call the conjugate acid and the conjugate base. The conjugate acid is the thing that would be the acid if you went backwards. The conjugate base is the thing that would be the base if you went backwards. But the easier way to figure out which one is which is to figure out which of these started as the acid. Whichever one starts as the acid ends up the conjugate base. The one that starts the base ends up the conjugate acid. That's probably a whole lot easier to figure out than picturing this reaction in your head flipped around the other way. The acid becomes the conjugate base, the base becomes the conjugate acid. So here we go. The acid became the conjugate base, the base became the conjugate acid. Conjugate acid and base pair only differs by one proton. When we say proton, we mean H plus ion. An H plus ion is just a proton when you think about it. It was a hydrogen atom which had one proton and one electron. If it has a positive charge, that means it lost its electron. So all that's left is a proton. So here we have the acid and the conjugate base. It's different by one hydrogen. Here we have a base and a conjugate acid. It's different by one hydrogen. There will always only be one hydrogen difference. If there's more than one hydrogen difference, it is not a conjugate acid-base pair. So, this is phosphoric acid. We said it had 3 hydrogens that it can get rid of, that it can donate. If this is the acid, the conjugate base is that, one hydrogen difference. You don't get rid of all 3 at once. You do one at a time. The conjugate base of that would be H1 PO4 2 minus. And then you do the conjugate base of that would just be PO4 3 minus. One hydrogen at a time. So here's an acid. What is the conjugate base?
HCO3.
HCO3 minus. When you get rid of that hydrogen, the plus goes with it. It's not all of a sudden you have too many minuses. So you have HCO3 minus. When you go from the acid to a base, remove a hydrogen, add a negative. So if you were going to take this another step further, what would be the conjugate base of that? CO3 2 minus. Remove the hydrogen, add a minus. What about H3PO4? We just did it. What is the conjugate base? H2PO4 negative. What's the conjugate base of that?
PO4 negative, 1 negative.
Just PO4 3 negative. You went from 2 negative to 3 negative, so we added a negative. What's the conjugate base of ammonium ion? NH3, remove a hydrogen. What happens to the charge? We add a negative, but we started positive. So it goes to neutral. Positive 1 plus negative 1 is 0. The charge is 0. And what about water? What's the conjugate base of water? OH minus. Does this make sense, going back and forth between them? You can go the other way. What is the conjugate acid of sulfate ion? Add a hydrogen and add a plus. HSO4 1 minus. Conjugate acid of that. H2CO3 neutral. -1 plus 1 takes you to 0. Conjugate acid of that. NH3 neutral. Add a hydrogen, add a +1 that goes neutral. It's this one.
Positive?
HClO2 neutral. Negative +1 is 0. And the conjugate acid of that. H3 for gaining hydrogen, PO4 neutral.
Can I ask a question?
Yes.
What about, like, for the first one, how it has a 2 negative charge,
Mm-hmm.
and you add a positive, it would just, it would go back to a negative, because it has 2 of
What
them.
is, completely forgetting chemistry, just thinking math. What is -2 plus 1?
Negative.
-1. That's exactly what we're doing. We write the negative after the 2, but that is -2. And so we add 1. So we have negative. So which, in this reaction, which is the acid, which is the base? Forget about the conjugates at this point, just worry about the reactants.
The base is the HCO3 minus.
Correct. So this gained a hydrogen, so that's a base. And so by default, that's the acid. And so if that's the base, and that's the acid, what is that? Conjugate acid. The base becomes the conjugate acid, the acid becomes the conjugate base. So really, if you look at this, and you can pick out one of them, just one of them, you automatically know the rest. Because Colin looked at that and he said that one's the base, so by default, that one has to be the acid. And the base becomes the conjugate acid, the acid becomes the conjugate base. If you can pick out one of them, you're golden. In the lab, in real life, we don't talk about protons and gaining and losing things. We talk about acidic and basic solutions. We talk about acids and bases in terms of solutions, not about what's in the solution. So we have to talk about what we mean by acidic solutions and basic solutions. In a neutral solution, you have the same amount of H3O plus as you have OH minus. Remember that these brackets mean molarity. So that's telling us the concentration of those things in our water. So this represents acid, this represents the base. So in a neutral solution, you have the same amount of acid as you have base. In an acidic solution, you have more acid than you have base, which means that you have more of the hydronium ion than you have of the hydroxide ion. In a basic solution, it's because you have more base than acid, you have more hydroxide ion than you have H3O plus. But that brings up a question. If you have a basic solution, if you take water and you add a base to it, let's say sodium hydroxide, why on earth would there be any hydronium ion in there? And looking at it the other way, if I have hydrochloric acid, why would there be hydroxide ion in there? And maybe even more confusing, if I have just water with no acid and no base added, why would there be both of them? It's because water is wet. Water on its own will form both of them. If you have a glass or a beaker of water, two water molecules can come together and transfer a hydrogen from one to the other. And if you do that, you get hydronium ion and you get hydroxide ion. So in pure water, even though it is neutral, there is hydronium ion and there is hydroxide ion. That's why water can act as an acid, because it acts like an acid. But that's also why water can act like a base, because it acts like a base and makes hydroxide ion. Mathematically, if we take the concentration of this and the concentration of that, and we multiply them together in any solution, we'll always get the same number. If we always get the same number, that means the constant. Constants we mark with K, and this is KW, K of water. At 25 degrees Celsius, room temperature, KW is 1 times 10 to the negative 14. This is a number you're going to need to know. But after a few slides, it's going to be stuck in your head. So you can circle it, but it's not something you're going to have to make sure you come back to later. So, if KW equals that, and so KW equals this plus times that equals that, in a neutral solution, that has to equal that. That's the definition of a neutral solution. In a neutral solution, they are both 1 times 10 to the negative 7. Don't worry too much about that number at this point. So this is KW. We said KW is hydronium ion concentration times hydroxide ion concentration, and it will always, always equal 1 times 10 to the negative 14. In an acidic solution, we have more of this than that. We have a lot of that. And so as this goes up, this has to go down so that this doesn't change. In a basic solution, let's say we add sodium hydroxide. We are adding hydroxide. As this goes up, this wants to go up. So this has to go down to keep that the same. So in a neutral solution, they're the same. In order for that to stay 1 times 10 to the negative 14, they both have to be 1 times 10 to the negative 7. In an acidic solution, we have more acid than base. So the hydronium ion concentration will be higher than that base level, that neutral level, and the hydroxide ion will go down. In a basic solution, we have more base than acid, so this will be lower than its starting point, and this will be higher than its starting point. But in all situations, KW didn't change. So, if we know H3O plus concentration, KW is always the same, so we can solve for OH minus concentration. All we have to do is know the H3O plus concentration, and we automatically know the OH negative also. It's just going to be KW divided by H3O plus. KW equals, they just solved for that. They divided both sides by that, and you get KW divided by H3O plus. Going the other way, if you know the hydroxide ion concentration, you can plug that in here and solve for that. So if you know one of the two, you automatically know the second one. So, if hydroxide ion concentration is 10 to the negative 5th, how do I find out the hydroxide ion concentration? Right. You're going to divide both sides by that, you get KW. What is the value for KW?
1.0.
Divided by that, which is 10 to the negative fifth. What do you get? These calculations use these exponents big time. They're all going to have these exponents. You're going to have to make sure you're really comfortable with your calculators.
1 times 10 negative 9.
1 times 10 times negative 9. So that's 1 times 10 negative 9. What happens here? All we have to do is substitute negative 12 in there. If you do that, what do you get?
0.01.
0, 1, which is 10 to the negative 2. Now let's go the other way. Here we know the hydroxide ion concentration, but we have to find H3O+. The math is exactly the same. We can still just put in 10 to the negative 6 here. And what do we get? Ten to the negative 8. Let's do the last one. We put 10 to the negative 12. And then negative 12 equals what? Do it, you're going to get 10 to the negative 2. Now, how was I doing that so quickly in my head?
Just subtracting exponents.
Yes. With exponents, when you multiply and divide, the exponents just add and subtract. So, in this here, if it's just 10 to the something, 10 to the something, the exponents have to add up to 10 to the negative 14. If we put 10 to the negative 7, and 10 to the negative 7, when you multiply those together, you just add the exponents. When you multiply powers, you add the exponents. So this is 10 to the negative 14. So here, I have negative 5. What does this one have to be so that the exponents equal negative 14? Negative 9. Negative 5 plus negative 9 is negative 14. Negative 12 plus what? Negative 2. Negative 6 plus what? Negative 8. And negative 12 plus negative 2. So if it's just 1 times 10 to the negative 5, because the 1 doesn't do anything, it's assumed, you can do it in your head. But as soon as you get 2 times 10 to the negative 5th, it doesn't seem like it's that much more difficult, but it is infinitely more difficult. Don't try to do that in your head. Okay? Then you got to use your calculator. Here's an example. You have 2 times 10 to the negative 8th. Do not do that in your head. Do it in your calculator. Times 10 to the negative 8.
Seven. 5 times 10 negative 7.
5 times 10 to the negative 7. Is that what everybody else got? Okay. So you did it in your calculator. I said don't do it in your head, but if you're comfortable, you can do it in your head, making a little assumption. Do it in your head and see if what you got in your calculator is close to. So what I like to do is just ignore that 2. Just say if that was a 1, what would my power be? That if I just had 10 to the negative 8, 10 to the negative 6, right? Negative 8 plus negative 6 is negative 14. And so because that's not a 1, my actual exponent is going to be 1 off. Either negative 5 or negative 7. We have negative 7, so it looks correct. So I assume it's correct. But if I did that check, and I said, well, if I imagine that's a 1, I should get 10 to the negative 10. And I calculate 10 to the negative 7, I know something's wrong. So here is another example. This one's not even in scientific notation. But all we have to do is stick it there. Stick it in there, what do you get?
2.9 times 10, negative 13.
2 times 10 to the negative 13. Yes?
So then, based off of that, would you say that that's a very acidic solution? If that's 2.9 times 10 to the negative 13, if it only goes 10 to the negative 13.
Well, let's think about it. Let's think about what the meaning of these exponents are. If we put this in the scientific notation, let's do it so that we can compare exponents. If we put that in scientific notation, what do we get?
3.5
times 10 to the negative 2.
We get 3.5 times 10 to the negative 2. So our base is that. Our acid is that. Which of these is the bigger number? The top one is actually the bigger one. Because it's negative, remember the exponents, that's telling us how many zeros to put in there. So the more negative our exponent, we have more zeros, our number gets smaller and smaller. So our hydroxide ion concentration is much, much, much higher than a hydronium ion concentration. So this is acidic or basic? Basic. We have more OH negative than we have H3O plus. But when you're working in lab, you don't know the concentration of either of them. What you know is the concentration of the solution that you made, and you have to figure out the concentration of one of the two so that you can then calculate the other one. But this is not hard. Here we have 0.1 molar HCl. Acid or base? HCl is an acid. What's it called?
Hydrochloric acid.
Hydrochloric acid. So, this is going to give us hydrogens. For every one of these that we have, how many hydrogens come off of it?
1.
1. So if you want to find the hydrogen concentration, you take the concentration of your solution and multiply it by however many hydrogens that you get. So in this case, it's 0.1 times 1 equals what? 0.1. Times 1 equals 0.1 molar. That is my hydronium ion concentration. So if that is my hydronium ion concentration, what's my OH minus concentration? How do I find the OH minus?
Divided by
Right. Plug in 1 times 10 to the negative 14. Divide it by that to get that. Because what is this in scientific notation? 1.0 times 10 to the negative 1. Negative 1 plus what is negative 14? 13. So the other one has to be negative 13. Here we have 0.1 molar sodium hydroxide. Acid or base?
base.
It's a base. So, when we dissolve this in water, we're going to get hydroxide ions. How many hydroxide ions do we get out of each of those?
0.1 mole.
We get one hydroxide from each of those. So again, it's 0.1 times 1 is 0.1. So the math comes out exactly the same. It's just in this case, this is now the OH minus concentration. And so if that is the OH minus concentration, this is now the H3O plus concentration. Everything just flip-flopped. We started with 0.1 molar acid here, 0.1 molar base. Everything is opposite. Here we have HCl again. All you have to do is plug this number in there. But this one you can probably do in your head. What is this in scientific notation? 1.0 times 10 to the negative 1, 2, 3, 4. Is that the H3O plus or the OH minus?
H3.
H3O plus, because we're getting, it's an acid, so we get hydrogens out of it. And so if that's the H3O plus is 10 to the negative 4th. What's the OH minus? 10 to the negative 10. Negative 4 plus negative 10 is negative 14. I'm going to add one more example. Let's go back to our 0.1 molar. We've got 0.1 molar H2SO4. What is the concentration of my hydronium ion? 0.2. In this case, we have 2 hydrogens. So we have to take the 0.1 times 2, 0.2 molar. That's the hard part. Once you know that, you just do your math. You're going to have to use your calculator this time because it's not easy head math. But going from that to that is the hard part. If it was H3PO4, you take 0.1 and you multiply it by 3. If we had if we had 0.1 molar calcium hydroxide, and I asked you the concentration of OH minus, what would you tell me? Same thing. We get 2 OH minuses off of there. We take 0.1 times 2 is 0.2. Don't forget to look at how many hydrogens or hydroxides you get from each molecule. So now we're going to take these concentrations and put them into something you're a little more familiar with. pH. These numbers are the same exact thing as pH. The pH gets rid of all of these funky exponents and lets us just deal with the numbers that add up to 14. So if we want to calculate the pH of a solution, we take the negative log of the hydronium ion concentration. Don't forget the negative. So I've got to have the negative. And make sure you are using log, not natural log. On your calculator, it should say log. Natural log is just ln. If you use natural log, it's going to give you the completely wrong answer. So you go negative log of the hydronium ion concentration. In the magic of logs, our logs take exponents and make them normal numbers. So if I take the negative log of that, does anybody know what you get? or you get to do it.
1.
You get 1. Take the negative log of that. What do you get?
5.
5. That one?
7.
That one?
11.
11. The log part gets rid of the 10, and the negative cancels out these negatives. And so a solution that has an H3O plus concentration of 10 to the negative 1 molar has a pH of 1. Just look at the exponent, get rid of the 10 to the negative. pH 7, pH 11, pH 5. Assuming these are H3O plus concentrations. Of these, we have 4 of them. Which ones are acidic and which ones are basic?
First two are
1 and 5.
1 and 5 are
Acidic.
acidic. What are these two?
Seven's neutral.
7's neutral,
And 7 is the basic.
Basic.
that one's basic. And so you can do it by looking at this. We said 10 to the negative 7 is neutral. Concentrations of H3O plus that are more than that are acidic. And as this number gets smaller, the whole number is actually getting bigger. So these are higher concentrations, so these are acidic. These have more acid. That one has less acid. It's basic. But now we can look at the pH scale. And the pH scale is what people use in lab. A pH 7 is neutral. Numbers smaller than 7 are acidic. Numbers larger than 7 are basic. So this is our pH scale. Everyone says the pH scale goes from 1 to 14. But that's not necessarily the case. If you do a problem and you get a number, an answer, that falls outside of 1 to 14, it does not mean it is wrong. What is the concentration, what is the pH of 10 molar hydrochloric acid? What's the concentration of H3O plus?
10.
10. 10 times 1 equals 10. What's the negative log of 10?
Negative 1.
Negative 1. Right?
Yeah.
Somebody take it, right?
Yeah, negative.
So that is outside of that range. So it doesn't mean it is wrong if something falls outside that range. These are some examples of things that are these different pHs. So pure water, completely pure water, not water out of the tap, is 7. Because for every water, when it makes a hydronium ion, it has to make a hydroxide. There's no way to not make 1 for 1. Things like ammonia that you have at home are basic. Salt water is normally a little basic. Milk, urine, beer, vinegar, lemon juice, stomach acid, those are all acidic. So this is what we're getting at. What is the pH of a 2 molar HCl solution? That's the negative log of 2.
Negative 1.
Negative 2.
Negative 0.30.
It's a weird number. Because it's not a 1, don't try to do it in your head. You can only do it in your head if it's all 1s. So negative log of 2 is negative 0.3, whatever I can say.
Yeah.
But it's a negative number. It's not in this range, but that doesn't mean it's wrong. Now let's look at this chart. When we go from pH 8 to pH 9, by what factor does the concentration change? Does it double? Does it triple? What does it do? What is the change there? So the concentration is going from 10 to the -8 to 10 to the -9.
Factor one.
Factor of the decrease, went from -8, 10 to the -8, 10 to the -9, decreased by a factor of 10. 10 to the -8, 10 to the -9, that's the difference of a factor of 10. That's what these exponents mean. So when we look at changes in pH, a pH change from 8 to 9 may not seem significant, but a pH 8 solution is 10 times more acidic than a pH 9 solution. All these log scales really take the giant scale that exists in the real world and condenses it into this tiny, neat little package. This is exactly how the Richter scale works with earthquakes. A Richter scale 5 is 10 times stronger than a Richter scale 4. That's why when they start to get up there, anybody live in California or someplace with earthquakes? When they start to get up there and you get into the 6th, 7th, and 8th, the difference in damage from a 7 is a lot more than the damage from a 6. Because a 7 has 10 times more energy than the Richter scale of 6. Let's go from a 4 to a 2. What is the factor difference there? From a 4 to a 2. Be careful. It's 100. You go 10 times 10 again. 10 times 10 is 100.
-100 just goes down, or just 100?
What is the 100? We say it's a 100. Yeah, I guess it depends on which direction you're going. If you're going from 4 to 2, the hydrogen ion concentration is actually increasing. Right? We go from -4 to -2. So it's positive. Don't be tempted to say 10 and 10, so it's 20. It's multiplication. So if we go from here to here, that's a factor of 1,000. 10 times 10 times 10. Here we took a soil sample, and we got the hydroxide ion concentration of 5 times 10 to the -7. What is the pH of this soil?
Is it 6? Or 6.30?
Be careful. It wants the pH. What is the formula for pH? Negative log of the H3O plus.
Oh.
This is giving us the hydroxide ion concentration. And so, if OH minus equals 5 times 10 to the -7, what is my H3O plus concentration? You're going to have to do it in a calculator because that's not a 1. One times 10 to the -14th divided by that.
2 times 10 to the -22nd.
-22nd? That doesn't seem.
Doesn't seem right.
I've got 2 times 10 -8.
Maybe that seems right. Probably an order of operation. So if that is my that's my hydronium ion concentration. Now I can take the negative log of that. To get the pH equals negative log of 2 times 10 to the -8 equals what? That seems right. 7.7. Like our K equilibrium constant, pHs have no units. So you don't have to worry about units here. pH, 7.7. Is this soil acidic or basic? Basic. Higher than 7 was basic. That's wrong. I see that every semester, okay? And I always think I go home and change it. Before that even came up, I said, I know I changed that last time. So if somebody's hacking into my computer and changing it, please stop. So we have to find the pH of each of these solutions. How would you start the first one? Is that going to give you the hydronium ion concentration or the hydroxide ion concentration?
This one, hydronium.
It's going to, this is an acid, and so we're going to take that number times 1 hydrogen, and so hydronium ion concentration equals, that's 8.5 times 10 to the 1, 2, 3, 4. And so, what is my pH? How do I find the pH? Take the negative log of that. pH equals .07. Done. Second one's a little bit harder, because what is this going to give us? It's an acid or a base?
That's a base.
It's a base. And so we take 0.01 times 1 to get 0.01 still, but that's our hydroxide ion concentration. So hydroxide ion concentration equals 0.01, which is 1 times 10 to the negative 2. So my hydronium ion concentration is 10 to the negative 12. Negative 2 plus negative 12 is negative 14. And I take the negative log of that. What do I get? 12. We do the last one. Here we have sulfuric acid. Is this going to give us hydronium ion or hydroxide ion?
Hydronium.
Hydronium. What is my concentration of hydronium ion? 2 molar. 1.0 times 2. We get 2 hydrogens. So we get 2.0 molar. So my pH is the negative log of 2, which is what? That's a calculator. Negative 0.3. We can also directly calculate pOH. The pOH is negative log of the hydroxide ion concentration. Same math, you just plug in the OH minus to get the pOH instead of plugging in the H3O plus to get the pH. And what that means is that pH plus pOH is always 14. Because the concentration of the two times each other is always 10 to the negative 7 times 10 to the negative 7, 10 to the negative 14. pH plus pOH equals 14. So, if my pH here was negative 0.3, what is my pOH? It's 14 minus negative 0.3 equals 14.3. If I have pH equals 3, what is my pOH? 11. 3 plus 11 is 14. If I have pOH of 8, where's my pH? 6. 8 plus 6 is 14. Getting back to the whole soil thing. Supposedly, hydrangeas will change color based on what soil they are in. My neighbor has a hydrangea bed, and there are both colors in there. Presumably, the dirt under them is the same pH. So I'm a little skeptical, unless he purposely changes them. But supposedly, I think blue is acidic and red is basic, but I don't know. You're not tested on that. We said to go from H3O plus to pH, we take the negative log of the H3O plus. Mathematically, if we want to go the other direction, we can do that. To undo that, we take 10 to the negative pH. To undo the pOH, we go 10 to the negative pOH. So if I take an easy example, and I say my H3O plus equals 1 times 10 to the negative third, what is my pH? Negative log 3. pH is 3. If I undo that, it says that I take 10 to the negative pH. So that's 10 to the negative pH. And that's exactly where I start. Do the same exact thing for pOH. So here we have a soil sample where the pH is 6.2. pH is 6.2. What is the hydronium ion concentration? We're just going to do 10 to the negative 6.2 equals what? If that's not a whole number, you have to do it in a calculator.
Times 10 negative 7.
Yeah. And so the reason you can't just put that is because, remember, scientific notation, these numbers have to be whole numbers. So you put that in your calculator to get it so that that's a whole number.
That's good.
So now we have tools to go between all of these things. We have this, in this box we have 4 corners. We have pOH, pH, H3O plus concentration, OH minus concentration. If you are given one of the 4, you can find the other 3. Say you're given that one. You can either go from here to here, and then here to here, and here to here. Or you can go from here to here, and then from here to here, and here to here. Or you can go from here to here, here to here, and here to there. It doesn't matter. As long as you get all 4 corners, you'll be fine. The more times you do it, you'll find out which ones have the easier math. To me, it's easier to work in pH and pOH because you don't have these crazy 10 to the things. You're dealing with real numbers here. So as soon as I get one of these 2, I immediately find the other one going directly. So if I was given pH, I would immediately find that one, and then I would go from here to here, and here to here. This math is the longest, most labor intensive. So I only do that one if I absolutely have to. It's really easy to go between these because they just add up to 14. And it's pretty easy to go from here to here. You just go 10 to the negative that. And 10 to the negative that will take you there. And now you've got all four, rather than doing this crazy thing up here. Does that make sense? In your homework, on the quiz, probably maybe the final exam, you'll get something just like this, where you're given one of the four and you have to find the other three. Here we have a lake. It says if the pH of water goes below 4.5. If it's below 4.5, is it acidic or basic? It's acidic. It wants to know, is the lake that we took this sample from alive or dead? We took a measurement and we got an OH concentration of 10 to the negative 9. Is the lake dead or is it alive? How would you figure it out? Which of these four do you have to have in order to figure out whether the lake is dead or alive? pH. We have to have the pH. So we have an OH minus concentration of 10 to the negative 14. So we have 10 to the negative 9. I don't know what I said. So this is 10 to the negative 9. And we have to get from here to here. We have two options. We can go from here to here, and here to here, or here and go this way. Which way would you rather go? Choose your own adventure. Do you want to go left? Do you want to go down? Who wants to go left? Who wants to go down? I'm with the down people. Both ways will work, but the down is easier math. So to go from here to here, we just take the negative log. If we take the negative log of that, what do we get? We get 9. So that gives us POH equals negative log of 10 to the negative 9 equals 9. If my POH is 9, what is my pH? 5. 9 plus 5 is 14. That's 14 minus 9 equals 5. So we went from one corner to the other. So the pH is 5, which is higher than 4.5, so the lake is alive, but I wouldn't necessarily want this one yet. In lab, we have a number of ways of measuring pH. And you're going to do 2 of these. There are pH meters, where it's just electronic, and you stick it in there, and it tells you the pH. They look almost exactly like the conductivity meters, the good conductivity meters that you use, not the little 9-volt battery ones. There's also pH strips that some of you might have used for pools and aquariums and things like that. Has anybody, when they were in high school or something, done water testing? Yeah. They probably gave you this little kit and sent you out. You had no idea what the heck you were doing, but you got out of class and you got to go play by the water and maybe push your friend in the river. And so what you were doing here is you were adding probably lake water or river water into here, and then you would add a dye and you would get a color. And then you held it up to a reference and you say, well, this color matches this color, and it says this color is pH 8, something like that. So you can do it any way. They all work. Our pH strips in the lab are a little bit different than this. Here there are 3 different little dots on the strip, and you have to compare it. What we have is just one big long roll of solid paper, and you dip it in and it just turns one color. Then you compare it to the colors on the container and figure out what pH you have. The liquid way, you're also going to do in lab. I think you already used phenolphthalein once in the reactions lab. That was when you added the liquid and it turned pink. Remember, you added phenolphthalein. When you would add some base, it would turn pink. You'd swirl it and it'd go clear. Add some more base and turn pink. You'd swirl it and go clear. And eventually, you added so much base that you reacted with all the acid and the whole thing turned pink. Phenolphthalein is a pH indicator. When you first put it in the water, it is an acid. When it's in its acid form, it has no color. When you keep adding base, it becomes pink. This is a titration. So this is sort of what you did. We're going to talk about titrations mathematically in a minute. But here we have an acid down here, just like you did. We have a base, and then we have a base up here that we're going to drip in. So it starts clear. The phenolphthalein is here, but because it's acidic, it's clear. We add a little bit of base. It turns light pink. Then we add more base, and it turns dark pink. We're not going to do these titrations in the lab, but what you use these for is if you have an acid. I tell you it's an acid, but I don't tell you what concentration it is. You then go on the shelf and you take a base that you know the concentration of, and you add it drop by drop until you hit this magic midway point right here. And at that point, the amount of base that you've added is exactly equal to the acid that was there. And so you can calculate the concentration of your acid. And there are a number of these dyes. So phenolphthalein, where phenolphthalein is here. What this tells you is that when you use it, you can only use it if the pH range that you're dealing with is here. Where it changes color is about pH 9. If you were looking for a pH change somewhere else, if you're dealing with river water or something, you would need to use something around pH 7, so you'd have to pick one of these. Everybody awake now? Let's take a break. We'll start at 7:30 on that clock.
That's why I asked. 6. Oh, 6, 7, or 8, or 8. Well, for this one. For more. Are you going to do that?
No, you have to use one of them. So, based on these prices, which one do you want to use? To figure out how many dollars it costs per. Okay, so that one costs $5.50, $9 per 500 grams. How many dollars per mole? Figure out how many dollars per mole that is. One of them is going to be a lot cheaper than the other one. We're 12 times 7 plus 1 times 6. So figure out how many moles that is. Figure out how many dollars. Say that comes up next week. You take the price by 3, you get the price.
Oh, and then I have one more question. So if you add an additional
That's the hardest one.
Okay, but for this, it says
One of this, just call it one. Huh?
Okay, so then when I was reading about the gardeners reaction vessel, that was that they have, like, that was one of the slides for.
That would be out of it.
I was thinking, I told you that.
Huh? How do you rate the value
Because these
recognition?
are all gases, increase the size of the vessel, they're going to stay at the concentration. So they're all going to go down, but the reaction.
Oh, you never had me back up, I'll show you that.
Okay.
Huh?
Never had me back up?
I went home.
So now, just to clarify.
Yeah.
Of that subway,
I woke up at 3 and I was about to hit you on that.
the sub killed you?
The sub, bro. Yeah.
Say that.
And I woke up at 3 and then go back to bed.
That's just those four.
Oh, then
Yeah, that's what I'm saying, yeah.
we're good.
That's what I'm saying.
That's actually really nice, so if you're going to add to the other side, it's gonna go up, and then the leftovers.
But I mean, if I get this done, I should.
Okay, yeah.
Now we just have to
Like, if you understand how to do,
Yeah.
I just think I want to get
Your employees got mad, or they were fighting what you said.
First over.
Well, look, now that I've been asked, it's like,
Oh.
how much that is.
That's like a picture. It's not hard, but
What do you have?
What'd you do, so now? That portion. Like, it's easy to be bothered by stuff.
I like the first stuff, but I like it. The last stuff that I said, even that, like, I have like,
I really think about it.
like, I have no choice if I want to,
I got every single one right.
You did that.
I got like
Oh, why do you want to sort out clients?
What was that?
How old are you?
That's just six variants. I know it's like crazy.
That was a good amount of food though.
I've heard of it. Some trees especially wolf farm. You get out of the stack days, you're like. Bro, good.
Okay, so I know the first one.
I mean, I read it. There are
What is the spelling number? Would it be the molar mass, the silicic acid,
But yeah, probably fuel.
silicic acid?
I will turn in last time.
Well, after 12.
You already turned it in? Oh, okay. Never mind. I just want to see one last question.
This has a big which question you take for me? See, I remember.
Let me.
I mean, we need over somewhere online. Okay.
Okay, we are almost there. We got like 10 more slides left, and then you're done.
Oh, that's not a lot.
So let's get it done. Okay? Yeah, we have a quiz. There's so much time.
How many slides are there?
There's like 10 more, I think.
Six.
No, 11.
60.
I don't know, we saw it on the campus, I don't know. I'm freaking out.
We're on 32, and there are 42.
Oh, okay. I was wrong. My bad.
So technically 9.
Okay, so on the last slide, we looked at, or I guess a couple, where'd it go? Here. We said, I called this a titration, okay, and that was a completely new word to you. Titration is when you take an acid and you add a base to neutralize it. Or you take a base and you add an acid to neutralize it. And so here, we're taking hydrochloric acid and sodium hydroxide, which is a base, adding them together. They're neutralizing each other. We call this a titration. Of the 4 types of reactions that we learned, which type is this? It's a double replacement. I think back then we said acid-base neutralization reactions were a specific type of double replacement, but I said don't worry about it. We're going to come back to acids and bases later on. It is now later on. When you add acids and bases, you always get water and a salt. And when I say a salt, in this case it is salt, sodium chloride, but you get a salt. And a salt is an ionic compound, remember. So when you add an acid and a base, you get an ionic compound and water. Here we have a strong acid and a strong base. That is the easiest possible type of reaction. It's the only type of reaction you're going to have to do though. If you have, say, a strong acid and a weak base, things get complicated. If you have a weak acid and a strong base, things are more complicated. And really complicated is a weak acid and a weak base. But you're just going to have to deal with strong and plus strong. And so if we know the concentration and the volume of either our acid or our base, it is very easy to calculate how much of the other one we need in order to neutralize it. In order for it to be neutralized, we have to add the exact same number of moles of acid as we add base. And so remember the formula for molarity. What's the formula for molarity? Moles over liters. And all day, as we've been talking about concentrations, what unit of concentration were we dealing with? Moles. So we were dealing with molarity of H3O plus, molarity of OH minus. And so that's this number here. And so if we know the concentration, and we know the volume that we have, we can calculate very easily the number of moles of acid that is in our solution. And so if we calculate the number of moles in our acid solution that equal completely neutralize it, we're going to have to add the exact number of moles of base. In here, to get the moles, you multiply this over here. So it's M times L equals moles. M is molarity, that's a unit of concentration. C stands for concentration. L is a unit for volume, it's liters. V stands for volume. In this case, the 1 and 2 don't stand for before and after. I think this is the same exact equation we had for dilution, but in that case we had one solution that was before and after. In this case, the 1s and the 2s stand for acids and bases. It doesn't matter which one is which, as long as you have the concentration of the acid and the volume of the acid together and the base together on the other side. I normally put acid 1 and base 2 just because I always say acids and bases. If I said bases and acids, I do it the other way around. So it doesn't matter. What you need is the concentration, the volume, and the volume of one of them, and one of the two of the other. So just like before, you're going to be given 3 of the 4 variables, just solve for the 4. So here's an example. It says, what is the concentration? Oh, jeez. I thought I deleted this one also. We're going to skip this one. This is a nasty. It looks simple, but it's nasty. So we're going to move on. Okay. Go home and try it. It's not going to be easy. We're going to do this one instead. So it says how much of a stock solution of KOH, and our KOH is a pH of 0.1, is needed to fully neutralize 13.4 liters of 0.2 molar H2SO4. So we have C1 V1 equals C2 V2. Which of those 4 variables are we trying to solve for? So it says how much. So it's one of the volumes. Which volume do you want it to be? We'll say we're looking for V2. So we're looking for V2, so we have to be given the other 3. So what is C1? Well, first of all, is the 1 in our case now going to represent the acid or the base? It's the acid. Because we said how much of the KOH are we looking for? And we said that is V2. So the 2 must be the base from here on out. So we're looking for V2, so we're looking for the concentration of the acid. What is the concentration of my acid?
0.2.
Be careful. It's 0.4. 0.2 times 2. So the concentration is 0.4 molar. What is my V1? 13.4 liters. So then I have to have C2. What is C2? We're given pH of 0.1. We cannot use the pH. We need H3O plus concentration.
Use the 14 subchat.
So that is 10 to the negative 1. I don't know what I'm doing. Say. That's our pH. We need to go 10 to the negative 0.1, which is what? Ten to the negative 0.1. Point 794. 794 molar.
Oh, yeah, accidentally did 10 times 10 to the power.
Yeah, funny story. When I was learning this in college, I did that same exact thing. I had a brain fart one day. I knew exactly what I was doing. I always used the little E button on my calculator. And instead of doing 1E something, I kept doing 10E something. So all of my answers were off by a factor of 10. But because I did so well in the class, the professor had started using my exam as the answer key.
Oh no.
So he got halfway through and said, why is everyone getting this wrong? And then he realized that I was wrong. So then he had to go back and regrade everything. Don't make my mistake.
That's hilarious.
So H3O plus here is 0.794. So now we have 3 of the variables. We can solve for the 4th. So C1 was 0.4. V1 is 13.4 equals C2 is 0.794 times V2. So E2 equals 0.4 times 13.4 divided by 0.794 equals what? I guess I didn't give you the answer.
I just have a quick question. I don't know if I might have the green part, but for if you wanted the C2, isn't the C2 for the KOH? So wouldn't it be POH? Wouldn't it need to be the POH of KOH?
Yes, thank you.
Okay,
Thank
just
you.
making sure.
She is correct. I am wrong. Because concentration 2 is a base. We need the OH minus concentration, not the H3O plus concentration. So we have to come back. We have to erase this. If the pH is 0.1, what is the POH?
14 subchat.
14 minus 0.1 is
13.30.
the OH equals 13.9. So then the OH minus concentration equals 10 to the negative 13.9, which is what?
1.26 times 10 to the negative 14.
So this is 1.26 times 10 to the negative 14 molar. And that is my C2. I'm going to plug this in here. It's a back.
4.254 times 10 to the 14.
4.24 times 10 to the
4.254 times 10 to the
54 times 10 to the positive 14?
14.
And what is the unit on that? This is, we're looking for V2. We're going to get out the same unit that we put in. Put in liters, we get out liters. 4 times 10 to the 14th liters. 10 to the negative 9th liters is a billion. 10 to the negative 12th liters is a trillion. So you're almost a quadrillion liters. Does that make, yeah, good question?
Would you have to have fixed for that?
Yes.
Would it be one or?
Yes, it would be one. So, 4.4. So stop and think, does that make sense? That is a lot. Normally if you get a number that's out in left field like that, it's probably wrong. But let's stop and think. Our acid is this, right? We're trying to neutralize our base. But look at the pH of our base. What does that tell you? What is the pH? Our pH of our base is 0.1. What does what is it, a 0.1 pH acidic or basic? It's acidic. And so we're trying to neutralize acid with a basic solution that's actually acidic. And so because it's acidic, our pOH was teeny tiny. And so you're going to have to add a whole lot of it in order to get enough of it to neutralize your acid. But in the meantime, you're also adding more acid, so in real life it never neutralizes. Let's do another example that's a little more real life. So let's say I'm in lab and I have a 2 molar hydrochloric acid solution and I have a 4 molar NaOH solution. If I want to neutralize, say I have 5 liters of that, how much of that do I need? So which of the 4 variables am I looking for?
2.
Looking for V2. So what is C1? 2. We're going to say the 1s are our acid. So we get 2 molar times V2, which is 5, equals 4 molar times V2. V2 equals 10 divided by 4, which is 5 divided by 2, which is 2.5. So we need 2.5 liters of it. That's more along the lines of the type of question you're going to see, at least on a quiz. As you probably figure out the homework and give your option crazy. At least the book homework. I don't try not to give you crazy things in the original, like Canvas homework. Okay, the very last idea we need to talk about are buffers. A buffer is a weak acid and its conjugate base, or a weak base and its conjugate acid, and they're going to be in about the same concentration as each other. So you're going to put two different things into your solution. They're this conjugate acid-base pair, and you're going to put about the same amount of each in. We have a buffer system in our blood. Our blood wants to be pH 7.4, 7.6, depends on which textbook you look at. So, we have to have a complicated system to keep it at pH 7.4. Because if you drink orange juice is acidic. That goes into your blood. If your blood was just water and you drink orange juice, your blood would become acidic and you would die. And you don't want to die. So we have this bicarbonate buffer system. So in our blood, we have bicarbonate ion and carbonic acid. Okay? And so if we take this, and we have equal amounts of them, and we add acid to that beaker, or our body, we add more acid. What we do is that acid is going to react with the conjugate base here, the base of the two, and it's going to make some of this. And so now we have a little bit more of that than we have of that. And so yes, our body or our beaker is a little bit more acidic than it started. But this acid that we added was a strong acid. We added a strong acid, it basically converted it into a weak acid. So it's going to minimize the pH change. If we go back to our neutral solution, and we add a base, this is a strong base, that base is going to react with the acid in our buffer. It's going to make more of our base. So yes, now we have more base than acid. Our pH got a little more basic, but it's a very small change versus if we just add the same amount of acid to water. Buffers resist pH change. That's what they do. That's their purpose. They try to minimize the amount of change in the pH. So in order to have a buffer, we said you have to have a conjugate acid-base pair. In back at the beginning of the lecture, we said a conjugate acid-base pair differs by one hydrogen. So if you are asked, if a pair of compounds can act as a buffer, what you want to do is you need to look at the pair and say, are these two things different by one hydrogen? So let's take this first one as an example. Is the difference between these two things one hydrogen? No. They're not even close to each other. I mean, they're completely different. What about this one? Is there one hydrogen difference between the two? Yes. This one has 3 plus 1 is 4. This one has 3. There is one hydrogen difference. So that this one can be used as a buffer. What about this one? Can this one be used as a buffer? Initial reaction is yes. It's different by one hydrogen. But we go back to our definition. You have to have a weak acid in its conjugate base. That's a strong acid. And so when you say, imagine this was a multiple choice question, and it asked which one of these can be used for a buffer system. You would say, well, do any of them have a strong acid or a strong base in them? And cross them off. That's a strong acid, that's a strong acid, and that's a strong base. So you can cross those off, and you're left with this one, and you say, is it one hydrogen different? If it's one hydrogen different, you can use it. If it's more than one hydrogen different, you can't use it. So, in our body, if this pH gets messed up, it screws up a lot of things. If our pH becomes too acidic, meaning it drops below that 7.4, we call it acidosis. And so if it's the process is called acidosis, you would call the patient acidotic. So a patient that is acidic, we say is acidotic. And if you have acidosis, you get all of these bad things. And you don't want any of those bad things. So you don't want your blood to become acid. In this situation, we have our carbonic acid here, okay? That is the carbonic acid in our blood, and that is our bicarbonate. So this is our blood. We have carbonic acid and bicarbonate. And it lives in the middle here as carbonic acid. If you have carbonic acid can break apart into CO2 in water. What do you breathe out when you exhale? CO2. You breathe out CO2. So taking what you know about equilibrium, if you remove CO2, is this equilibrium going to shift left or right? Left. It's going to, if you take this out, it's going to shift left. You have now removed acid. So when you breathe out CO2, you are basically breathing out acid. When your body metabolizes food, it makes acid. So your body makes that, it combines with the carbonic acid in your blood, or sorry, the bicarbonate ion in your blood, to make carbonic acid, and then you breathe it out as CO2. Your body is constantly making acid, and you're constantly exhaling. So, someone who has acidosis, the pH is going to be less than 7.4. And there are two types of acidosis. There's respiratory acidosis, and there's metabolic acidosis. The respiratory means that there's a problem in how much CO2 you are getting rid of. It has to do with how fast you're breathing. If someone is too acidic, do you think they are breathing too fast or too slow? Too slow. Because if they're breathing, the purpose of breathing is to get rid of acid. If you breathe slow, you don't get rid of enough acid, and so you become acidic. Metabolic acidosis is a kidney problem. Your kidney makes the bicarbonate ion. And so, if you are acidic, is your kidney making too much or too little of the base? Too little. Kidney makes base, you breathe out acid. So if your kidney isn't functioning, you don't make enough bicarbonate ion, and even if you're breathing normally, you become acidic. So with respiratory acidosis, you're not getting rid of enough CO2. Metabolic acidosis, you're either not producing enough bicarbonate, or if you have a metabolic problem, how much food your cells are breaking down, you can make so much H+, so much acid that your kidneys can't keep up. So, if you were acidotic, what can you do in the short term to help fix the problem? Can you fix your kidneys? Can you fix your kidneys? No. You can't fix your kidneys. Can you change how much acid your cells are making? Not very easily. What can you change in this system? How much you breathe. I can breathe slowly, I can breathe fast, I can control that. So if I am acidic, if I have acidosis, do I want to breathe fast, or do I want to breathe slow? Fast. I have too much acid in my blood, I want to breathe it out. I want to breathe it fast. What's a situation that a patient could have respiratory acidosis, where they are not breathing fast enough? Why would someone not be breathing fast enough? The lungs are damaged, So in that case, maybe they are breathing fast enough. Maybe they're breathing as fast as they possibly can, but their lungs just aren't working. What else? What about an really old person? They just can't breathe fast. And their lungs probably aren't working at the same time. So they're breathing slowly, and their lungs aren't working very well. The opposite of acidosis is alkalosis. Alkaline means basic. Alkaline is the same word as basic, or a base solution. This is pH over 7.4. And again, we have respiratory and metabolic alkalosis. So in respiratory, that should be alkalosis, that word right there, alkalosis. I swear somebody switched this lecture. So if this is alkalosis, you're exhaling too much CO2. Why would someone be exhaling too much CO2? Panic attack. They're breathing fast for a reason that has nothing to do with actual breathing. It doesn't really make any sense. It's a mental thing. Their brain is telling them to breathe fast for a reason that doesn't actually exist. So they're breathing fast. What do people do when they have a panic attack and they're breathing very fast?
Deep breaths.
Take deep breath. They force themselves to slow down. Or what else? I see it more on TV shows than on actually in real life. Breathe into a hopefully paper bag, not a plastic bag. Because the plastic bags say don't inhale them, right? And so, if you slow yourself down, you're going to eventually correct the problem. What does breathing into a bag do? You take back in the CO2. You're getting rid of too much, you're breathing out too much CO2, but then you breathe it right back in. And so you kind of correct the problem you correct the symptom without correcting the root problem. In metabolic acidosis, either your cells aren't making enough acid to keep up with your kidneys, or your kidneys can be making too much base. So, if you are alkalytic, you are basic, you have pH more than 7.4, how are you going to fix your problem short term? Breathe slower. So the breathing is a short-term fix. You can do that, but you're not going to purposely breathe slower for the rest of your life. Right? You're not going to purposely hyperventilate for the rest of your life. You've got to fix this problem or the reason why you're already not breathing correctly. There are a couple other buffers in the body, but they're very minor compared to the bicarbonate. Bicarbonate is by far the biggest one. There's also a phosphate buffer, and then hemoglobin itself can actually act as a buffer. Is that the last one? Yay. Okay. So we got to go over the homework.